Welcome everybody to EarthShift Global's next Brown Bag webinar with John Cerrucci. We're looking forward to hearing him talk today. And John, would you please share your screen? I've been running a loop of his. Welcome, John.
Yes, hello. I'm getting a message I cannot share the screen while other participants is sharing right now.
All right, I'll stop my share and you shall go ahead. Try it now.
All right, that seems to work. How's that?
There we go. Perfect. Okay, well, if you would take it away. I've had the loop of your bio out on the screen, so everybody should be familiar with who you are and what you've been doing, but please feel free to elaborate any.
Okay, very good. Well, welcome everyone. My name is John Cerrucci. I guess I'm a geographical engineer or an engineering geographer or something like that I've sort of invented based on the fact that I've taken a fairly keen interest in geospatial analysis in the last 10 years or so. And in particular, I'm interested in its application in visualizing data and using it to make better decisions, which is the subject of our discussion today. The title GIS-Based MCDA has a lot of acronyms. We'll try to make some sense of that, step through what they are, and share some examples. Let's see. You seeing the screen advance there?
Yes, we are.
Okay, so I'm going to assume that the participants may not have too much knowledge about GIS and MCDA, so I'll be providing a brief introduction to GIS, Geographic Information Systems, and to multi-criteria decision analysis. And then we'll put that together as GIS-based MCDA, talk about some examples and applications for spatial decision analysis. All right, let's start with GIS. GIS is a geographic information system, which is inherently a decision support tool. And in a GIS, geographic data, that is data that has a location aspect to it, is brought together in a relational database and transformed into a mapping system so that we can visualize the information, look at trends, evaluate patterns, and understand relationships. So it's a matter of converting data that has a location aspect into useful information. Geographic information science is that discipline of using these GIS tools and methods to address scientific questions. We have to talk about maps if we're going to talk about GIS. GIS is not a map is not GIS. However, most modern maps are now created using a geographic information system. And a map is usually the way that we relate a lot of the results from GIS analysis because it's a very useful way to visualize data that is spatial in nature. I would posit that the map is our oldest form of model. Long before this clay tablet was made in Babylonia, we could imagine some prehistoric ancestor of ours took a stick and drew something in the sand to show where she found some food source. And so we use maps. We've used them throughout our history. We relate to them because we are spatial thinkers. We're designed to think in terms of where we are relative to other things. It's been important in our lives throughout evolution. And when we look at a map, we're relating that spatial context in our brain into something that makes sense to us. As a model, a map is inherently wrong. It's flawed. It's a gross distortion of reality, but it's useful to us. The way in particular maps are distorted is because they represent reality with almost all the information removed except for a few pieces of data which is helpful to us at the time. So let's dive into that a little deeper. Again, as a model, the map is kind of the output of a GIS, and usually the way we think about the data that's in a geographic information system. If we characterize the data in a GIS, it's stored in one of two formats, either as vector data or raster data, as shown here. Vector data is represented as points, lines, or polygons. In raster format, the area of consideration is divided up into uniform area cells, and each cell has a unique value associated with whatever data type is being considered. In either case, all of these locations have a connection through a coordinate system with some real place on the planet, either our planet or some other planet. So they're georeferenced, we say, to a coordinate system. It could be latitude and longitude. There are many other coordinate systems that bring them back into the real world. One of the distortions in a map is the world is inconveniently not flat, and therefore to get them into a flat map, we have to do some things in terms of projection, which stretches the data in a way that we can put it onto a computer screen or a piece of paper. Another concept I want to relate to, which is kind of typical in terms of thinking about geographic information systems, the idea of layers, and that's shown over on the right-hand side here. This is from the U.S. Geological Survey national map, showing how different types of data, from including physical data and other things like geographic names, can be piled on top of each other. And so when we think about a relational database, as we drill down vertically through this, in a GIS, we can relate data of different types which happen to reside in the same place together and actually do processing steps between them. In the horizontal plane, for a given type of data, we can look at its relationship spatially with other like data in proximity to it. Just developing that a little further here, in the background is a map portraying the location of energy from waste facilities in the United States. And in this case, they are represented as point data, vector point data. Associated with them is an attribute table. And as shown here, each of the rows in this table represent a different location. So they're called features. If we looked at, for example, let's just say point 11 is Wheelabrator Bridgeport Company energy from waste facility in Bridgeport, Connecticut. And associated with that feature are all these different columns or fields of data. So in a GIS, we can combine an awful lot of information together. It's a great way of packaging stuff, associating it with a place, but bringing it together all into one place. We can have dozens of different fields, essentially creating an array upon which we can perform various operations, much as you would with an Excel table, for example. Some of those operations are, we start with data preparation. We have to, as I mentioned, project it into a flat form. We have to reference data which doesn't already have a spatial context. When you put an address into Google Maps, it tells you where to go. That address doesn't have a location on the Earth until it's georeferenced to some coordinate system. And behind the scenes, that's what Google is doing. Once we have all that data together, we can query it like any other database. We can also do basic processing step, combining data together, merging it, aggregating it in different ways to make it simpler or better to understand, looking how data intersects spatially. We can perform operations between the different layers, doing overlay operations, adding them together, doing mathematical processes. If we have a layer that has to do with, has a population count, and we have another layer that has an area within a boundary, we can divide the latter into the former to get a population density. Simple things like that, very straightforward to do and typical to do. We can also extract information that's useful using conditional analysis based on its location or based on the data's attributes. We typically perform distant operations. How far is this from that? We can look at creating buffer zones, and as shown here in this graphic around a creek, what various distances away from it. Maybe that's a study area. We want to look at what's growing there, what lives there, or consideration of the area of a floodplain. These are all very traditional things that were done using a GIS. However, we can do more complex things as well. And I've quoted Waldo Tobler up in the upper right corner. Everything is related to everything else, but near things are more related than distant things. This is, has been coined as the first law of geography. It seems rather elementary, but it actually is very important from the standpoint of the statistical analysis of spatial data. One of the characteristics of spatial data that makes it distinct is that it is highly autocorrelated. If I'm standing here and you're standing 10 meters away from me, we probably have something in common. And the conditions at those locations probably have a lot in common. So you have to contend with autocorrelation when you're doing statistical analysis, and it's automatically built into spatial analysis. So that has sort of created a distinct set of statistical methodologies associated with spatial treatment. They include looking at surfaces, considering densities, point pattern analysis, considering whether things are randomly distributed, or if not, how are they concentrated, where are the hot spots, performing interpolation. We always have incomplete information. We get data at certain points. We have to fill in the gaps in between. When you look at a temperature map from the meteorologist, they're not measuring temperature everywhere. They're measuring it at temperature stations and interpolating between that to understand where the temperature and pressure bands are. We do trending along those surfaces to understand how things are moving, sloping, or changing over distance. We can perform focal operations to look at what's in the neighborhood of a point and process the information in that neighborhood, perhaps to aggregate it in certain ways. In addition to the basic math on overlays between layers, we do more complicated things like considering fuzzy membership and weights of evidence. And of course, we are always interested in spatial networks. This could be roadway networks, pipeline networks, power line networks, hydrological paths when we look at a surface, and we can do analysis on that using a GIS. All of this is often used to serve making a decision, and hence our interest in applying GIS for multi-criteria decision analysis. One of the reasons why GIS has become much more ubiquitous in the last couple of years is because of the wealth of information out there, much of which is spatial in nature. We still have to go out into the field and get information the old-fashioned way, but more and more so, we have access to a lot of information remotely through remote sensing. There's a wealth of imagery information in the visible spectrum and many other spectra. The Earth has been scanned countless times over every square centimeter of it. And surprisingly, a lot of that information is publicly available. There's remarkable resources. Some of those resources are things that you'd expect, like the US Census Bureau information, but other things like social media also have a spatial context. If you weren't aware of it when you tweet something, unless you've changed your privacy settings, you're also identifying where you're tweeting from. And that goes out into the public domain, and people are using that kind of information to do market analysis, to understand trends and patterns, and even doing unique things like dealing with emergency situations or identifying trends in epidemiology, all from extracting and processing spatial information that comes from social media. So this is one of the reasons why GIS has become very prominent, is because it is a very good way of processing all this information that we now have available to us, particularly that information that's spatial in nature. There's a lot of different tools that can be used to do that. The dominant software used in GIS is ArcGIS from ESRI. These are the big guys out there. I don't know what the exact numbers are, but I would expect that more than 80% of the GIS work is done with tools from the ArcGIS suite. However, there's a lot of other available tools out there, including some free and open source systems like QGIS, which also has a desktop platform that does many of the same things that the basic ArcGIS desktop software does, and it's actually quite good. You could do things like using the R platform for statistical analysis. There are spatial packages that are not very intuitive, but actually very, very effective. And associated with these basic desktop tools are many other things that allow the maps to be made interactive and put out on the internet, presented in different ways. So a vast and growing field of different things out there, all complementing the ability to treat spatial data. But again, I guess the takeaway here would be, if you're not familiar with it, probably a logical starting point is to familiarize yourself with ArcGIS by ESRI, or if you're on a budget, QGIS. So now let's switch gears and talk about decision analysis, multi-criteria decision analysis, which I'll refer to as MCDA. As you can imagine, we're always making decisions. We're making decisions countless times throughout the day. Most of those decisions we don't really give a lot of thought to. They're simple. They may involve multiple criteria, but those are implicit when we consider what we're going to wear for the day. It's not a long, drawn-out process, but we give thought to where we're going, what the weather's like, and so on and so forth. The other aspect in most of the decisions we routinely make is that we're the only person involved in making that decision, which greatly simplifies the process. When we talk about MCDA, we're talking about a collection of formal approaches whereby multiple criteria are considered explicitly. And this is usually done, or almost always done, when the decision has a high impact. Justifies that type of effort, and it's complicated. The ways it can be complicated are when the criteria conflict with one another. There are trade-offs in the decisions, and when there are many stakeholders who have different viewpoints and different valuation of that criteria. Now, many decisions are spatial in nature. They can be explicitly spatial, that is to say, the actual decision outcome is choosing a location, where they can be implicitly spatial, in which the criteria itself has some kind of spatial characteristic to it. And as I mentioned earlier, GIS is a decision support tool. So it's quite logical to bring together GIS and MCDA disciplines, and that, in fact, is an expanding field. This is a somewhat dated review summary of GIS-based MCDA peer-reviewed articles by Jacek Malczewski. It goes back to 2006, but the outcomes are still very relevant now. And in this matrix, we see decision problem types and application domains. The numbers are simply paper counts. And so I sorted this to kind of see where what seems to be trending, and in terms of decision problems, it's to no surprise things like site selection, land suitability analysis, resource allocation. In application domains, the traditional GIS areas like environmental applications, urban planning, forestry come up. Not surprised to see things like transportation, but also hydrology analysis, waste management consideration. Farther down the list, but I think underserved areas include manufacturing, which can really benefit, real estate, of course. So I don't think there's any surprises on here, but this is kind of a map, so to speak, a table of the trends in MCDA using GIS. And it seems to be accelerating. Probably because of the availability of big data, familiarity with GIS, and more real-life application of MCDA techniques. Okay, let's go a little farther into MCDA. This is a very general flow sheet of the process steps. Starts off with identification of a problem, and then the problem needs to be structured. So what do we mean by that? That's really spelling out what are the criteria that are going to be considered in the decision process. What are the different alternatives? We're going to choose between A or B, or between a whole series of different possible options to select what we believe is the best. We need to characterize what we know and don't know. What are the uncertainties? Who are the stakeholders, both the decision makers, but other people who also will be weighing in on the decision in some way, and defining external factors and constraints. Once the problem is structured, then you move into kind of the core of processing this information in model building, where decision rules are applied in some way to take the information about these criteria, their values, and put them together in a way that allows us to somehow relate the different alternatives to one another, either providing a score for them or ranking them in some way so that the decision makers can value which are the preferred alternatives. This information then, it's not a matter of feeding it into the computer and getting an answer. It's getting useful information that decision makers can apply, sometimes iteratively, going back into problem structuring to finally extract something that they can put into an action plan. We're going to go a little farther into the decision rules now, and I'm going to give a couple of common category representations. There are many, but these are some ones that are fairly easy to understand and commonly used. The first category of decision rule is in value measurement, and so I'll describe this in terms of this cartoon. In value measurement, for a given alternative, let's say alternative 1, the quantitative values of criteria are combined in some way by perhaps doing some processing steps where they can be normalized and weighted and then combined together in some way to get a value for that alternative, considering all the relevant criteria. This is then done for all the alternatives, and then they can be compared and ranked or scored in some way. Typically, they're combined in the criteria of information is combined in something like a weighted linear combination, where they're the product of their values and weights are summed. And this is easy for us to follow. Software tools readily do this, or we can create them in a GIS. Raster math techniques are directly applicable to do this kind of processing between different data types. However, the outcomes, it's been said, do not necessarily represent the way we really think about decisions. That's one of the criticisms of this approach, despite its logic. Another rule category is a reference point, or sometimes called ideal point. And in this case, again, I'll refer to the cartoon. Starting off with a criterion believed to be the most important, a reference level is selected subjectively by the decision makers, and alternatives are compared to this reference level to establish whether they meet the reference level, either they're above it or below it, whichever the way it works, and thereby eliminating alternatives that do not satisfy the reference level. And then we go on to the next criterion and so on down through all the criteria, basically filter out alternatives, ideally arriving at some remaining alternatives that are suitable for what we want to accomplish. This can be done iteratively, because usually when you do this, you may not like the answer or learn something about the way you are valuing criterion, and therefore you iterate back and adjust these reference levels accordingly. Very, very straightforward to do this in a GIS using overlay techniques. Essentially, some of the first GIS analysis was doing just that, attribute by attribute, filtering out the information that doesn't meet a certain requirement. It's inherently good for initial screening. To be done beyond that, again, it requires this iterative process of adjusting reference levels, because you may not get one alternative, you may get no alternatives or many. And therefore, it may not, at least in a straightforward, linear fashion, be appropriate for rigorous analysis. A third category I'll mention briefly here is outranking. And in this case, alternatives are looked at pairwise. Instead of trying to put a value around criteria for a given pair of alternatives and a criterion, one alternative is considered subjectively by a decision maker to be either better, worse, or indifferent relative to the other alternative. And then that's also done for the next criterion, and so on for all of the criteria for that pair. And then that process is repeated for all of the pairs of alternatives, and possibly done by every stakeholder. And with all that information and categorization, there's techniques to then process that information and extract from it an overall categorization of the alternatives, ideally coming forward with some of the alternatives which are deemed to be the best. It's a way of effectively eliciting the stakeholders' valuation in a more accurate fashion than just asking people to assign weights. It's highly interactive, which is good and bad. It doesn't work well when there's a large number of alternatives just because of the computational intensity, but it does help to ferret out ambiguity and deal with that. However, it's very labor and computational intensive, requires a considerable amount of patience, I guess, by the stakeholders. I mentioned before, there are many decision rule models, and those models are embedded in methodologies that are constantly changing, being developed. Operations research has dealt with decision sciences now for decades. It continues to evolve, and there's lots of different places to go with this. I just tried to capture some of the high level and basic categories in those three examples. Now I am going to give some specific examples. Two literature examples I'll cover briefly, and then one example from my own work that I'll go into a little bit more detail. The first one is a land suitability analysis for siting agave that is intended for bioethanol production. Agave is recognized as a potential available commercial crop that could be used for bioethanol and has the advantage of being fairly hardy and will grow in semi-arid climates, so therefore may represent less competition with food crops. And in this case, work done by UC Berkeley and Berkeley Labs, they considered several species of agave relative to criteria associated with topography, climate factors, soil factors, and solar radiation. And then taking a value measurement approach, aggregating that information together. The unique thing they applied here, as opposed to just doing something simple like a weighted sum, which has its flaws, as I pointed, they took a fuzzy membership approach where the suitability of these criteria was considered to be either suitable or not suitable, or somewhere in between based on some functionality to extract expert knowledge from the decision makers. And that subsequently went through a couple of other statistical steps to combine it in a way more effective than simply taking a sum or product of these attributes to ultimately aggregate it into evaluation for each alternative. And then as a final step, although they didn't call this out explicitly, they essentially applied then a hybridized reference point analysis to further restrict and filter out data that didn't meet several other constraints. And the results are, as shown here, and easily visualized in a map, areas which met the suitability requirements and constraints for agave as a bioenergy crop. Second example is in housing development siting. GIS is often used in urban planning. This is a rather more rigorous example of how a site selection could be formed using an outranking method. In this case, these folks in Switzerland considered the criteria shown here, both environmental and physical characteristics as criteria, and went through this process of doing a pairwise comparison where they rated the criterion for each alternative pair as favorable, unfavorable, or uncertain. The unique thing they did here is, I mentioned earlier that this outranking method doesn't deal with a large number of alternatives. When you're looking at siting studies over an area, you virtually have an infinite number of possible point locations, and that's undoable when you're doing a limited number of wise comparisons. So in their case, they use some techniques to create homogeneous zones based on the characteristics of the criteria to limit the number of alternatives and therefore making it effective to apply outranking. The third example I'm going to describe is some work that I did associated with waste transfer station siting. What's a little different here, as opposed to simply applying MCDA in terms of looking at a forward-looking decision, I applied it in a way to investigate and interrogate previous decision history to try to understand what went into those decisions. A retrospective decision analysis. And in doing that, I applied several different decision rule models. Waste transfer stations are facilities where municipal solid waste is brought to from its source and temporarily stored before it's loaded onto large haul vehicles and taken somewhere else. Sometimes other steps like separations and processing are done here, but the principal purpose of waste transfer station is to get it from small trucks and put it onto large trucks. And this is a classic MCDA problem with competing criteria. You put waste transfer stations somewhere between the sources, residences and businesses, and the ultimate disposition of that waste, which could be a landfill, incinerator, or energy conversion facility. Where you put it depends on a number of things. The reason you have it in the first place is because it's very expensive to drive these small trucks a long ways. So it's much better to put it in lower labor costs, lower fuel costs, to put it into large haul vehicles. However, there we go. That's what I wanted to do. However, there's some competing criteria. So if it's merely economics, you want to, and quite frankly, some environmental factors, you want to get these waste transfer stations close to where the population is, where the waste is coming from. However, no one particularly wants one next to them. No one wants to deal with the traffic and noise and odor issues. Furthermore, these are probably places where real estate's most expensive, so that tends to drive it away. So these competing factors have to come together in terms of making a good decision on siting waste transfer station. In order to look at this problem retrospectively, we can't just rewind things because we're not working with the decision makers, in this case, many different decision makers for multiple decisions. So we kind of have to work both ways and work our way inwards to the model building step, making some assumptions around how the problems are structured based on best practices and literature history, but then working back from the actual results where waste transfer station is actually located. For this case, we focused on Los Angeles County. It's a highly populated county, has a lot of waste, has a lot of waste transfer stations, and has 41 of these large volumes transfer stations that have more than 100 tons per day of waste. So clearly these are high impact siting decisions. In terms of alternatives, as I mentioned, when you're looking at citing a point location, you virtually have an infinite number of possibilities. To discretize that, we divided the county up into 1 hectare area cells, which more or less corresponds to the average footprint of this size of a waste transfer station. And that yields about 1 million different possible locations for waste transfer stations, of which 41 have waste transfer stations cited at them in LA County. In the problem structuring step, we have to consider the criteria. For this, we applied the guidance for waste transfer stations. Of course, all the distance information about road network and physical characteristics, the land, zoning, and land use. We, because it was a point of interest in this study and understanding how other things might come into play, included a number of demographic factors for consideration. All this information had to be pulled together and aggregated and brought together into a form where it could be compared ultimately as a raster. Many other transformation steps, I won't go into them other than to say, expect when you do this kind of stuff, you spend about 80% of your time doing data processing. That's just the nature of this kind of analysis, bringing it all together. And ultimately, I guess the final processing step outcome is an enormous array of characterizing the criteria at all these locations, 1 million of them, across several dozen different criteria that will be considered in statistical analysis. And now we have all this stuff in a form that we can start to some statistical work with. So to do this, we have to basically fit that data into different model forms. And we looked at value preference and reference point model forms to try to understand why 41 of the potential 1 million locations in LA County seem to be the best ones for siting waste transfer stations. And I might mention this work was, these transfer stations were siting over a period of time with different municipalities. So there's a lot of individual specific decisions that were made we can't characterize. What we're looking for is to try to identify the commonality between them and understand trends and themes. So looking at value preference, considering a weighted linear sum approach to aggregating information, we can fit the data directly to that. We have to put the model form in a logistical model form in which the outcome, the outcome either goes to limits of 1 being yes, this is where a waste transfer station resides, or 0, this is not a likely place for a waste transfer station. And that's just a matter of statistically crunching through all of this stuff to develop what amounts to a probability model. And what we learned from that is a number of criteria were definitely significant non-collinear. You want to try to minimize the number of criteria that gives you a good model fit. And no surprise, travel time between residents and the disposal at a landfill came out as the top factors. In fact, we now can quantify, based on this decision history, where the sweet spot is in terms of citing these places. However, we also identified that there was correlation, significant correlation, with a lot of interesting demographic factors such as racial mix, income level, and age. Now, I put in bold there, correlation does not imply causation. I would hope that decision makers did not necessarily consider these things explicitly. However, they may be related to other factors like real estate costs that came into play here. And this is very useful information in terms of interrogating a past decision history. We can take this model and overlay it on our area of interest. And what you see here in the darker blue-green areas, these are areas that have a higher probability of having a waste transfer station based on the previous decision history. And we get very good fit with the actual location of the transfer stations. And this can be used to suggest where, if things are not changed in the way decisions are made, where future waste transfer stations could also be cited. Now switch to looking at this from the reference point decision rule approach, where we try to discern if there's some kind of threshold reference level based on the value for all of our criteria to explain why the waste transfer stations are put there. This was not so matter of fact to work through how to derive this as in terms of a simple regression. We had to do some creative things using relative frequency Pareto to try to find these imagined reference levels, and ultimately created a satisficing model, not a probability model. I'll explain. We'll come back to that, but in fact, we're able to derive reference points for a number of the criteria. They did not correspond one-to-one with those from the value preference criteria, and some of the criteria that clearly appeared to be significant from the value measurement approach were not revealed here as having a reference point. But we were able to create this satisficing model. So satisficing model means in this case, you can see the green areas are where the reference points that were identified were met, and the lighter areas are where they're not met. Not such a great fit in this case. About 50% of the waste transfer stations actually didn't fall into a satisfied area. So a little bit harder to believe that this was a credible way of explaining the decision history. So in comparison, using a value measurement, a value preference decision rule, able to get a pretty good probability model that fit very well, identified some surprising social criteria that were correlated, and therefore this is actionable. If the decision makers or other stakeholders or community members have reason to be concerned about this, they can use this as a way of quantifying the past decision history, and therefore using it as a way of changing the approach in the future if those results are not in keeping with their value system. The reference point decision rule, not so good in this case. The satisficing model didn't explain the location of waste transfer stations very well. It was an inadequate fit. And I think what we learned from this is that this type of fit would be better for decision histories that have a much more limited number of well-defined criteria. I'm going to wrap up here just by making some comments on other areas we might look to apply GIS-based MCDA. The decision types shown over on the left-hand side would certainly include any kind of facility siting. This could be a manufacturing facility, retail outlet, could be a waste processing plant or waste transfer station, of course, a warehouse. Also, we don't have to necessarily look at a point location. It might be a transportation route or a pipeline route or electric power route. GIS-based MCDA is very relevant for urban planning and land preservation work, and any sort of raw material sourcing or other supply chain optimization, such as where to put the warehouse. As I showed in the retrospective analysis, we can use it to interrogate past decisions, so therefore it's useful for competitive analyses. And you can certainly believe that the military uses GIS extensively in intelligence operations to do just that, where competitive analysis has particularly high stakes. Characteristics of the kinds of decisions that you'd want to do this much work necessarily have high impact and or high risk. You're just not going to invest the resources and time, effort, and cost unless that's the case. But you're also looking for decisions where there's trade-offs, there's competing criteria. They can include the traditional criteria, trade-offs between economic and social factors and environmental factors, but also where we have diverse views from our stakeholders. There are techniques that can be applied to deal with qualitative attributes and bring them into a form where we can rigorously evaluate them. We're always dealing with incomplete data and often large uncertainty. So this is where the more high-powered statistical analysis tools and MCDA techniques really are useful. So that's what I've got for today. I'd be pleased to welcome any questions.
Wonderful, John. Thank you. You explained everything so very well, and your graphics were just spot on. I have a few questions here. I'll start with the first on slide 13. The papers on GIS and MCDA has a column called Impact Assessment, and this person is wondering whether that is the same as Impact Assessment in LCA.
Here. I can say with pretty good certainty that it is not, because I didn't see anything really in, this is from Jacek Malczewski's work, where he really dove into any kind of life cycle assessment analysis. So I don't think it was specifically around an environmental impact assessment, but probably more a generic description of that.
Okay.
However, I would comment that I do believe that in terms of life cycle assessment, there's really a need to consider the spatial context, because traditionally we look at impacts to the, we cross some border and we go into the environment, which is the rest of the world, and we don't consider the fact that in terms of stakeholders' viewpoints, location matters. If it's in your backyard, or if it's not something which is like a greenhouse gas uniformly distributed in the environment.
Okay. At this point, I also wanted just to remind our listeners, if you would like to send me any questions, Holly Harris, via chat, I will relay those to John. And I have a few more questions here. what was the goal of the transfer station study, and what question was there a specific question you were trying to answer?
Um, well, yes. I mean, it was a case study. So in part, it was to develop and evaluate this methodology because it was a unique approach to look backwards and try to do this work retrospectively. But relative to the case study itself, we were trying to discern whether we could come up with a rule set that basically described the decision history. And in particular, we're looking to see if we could find any surprising things that were not in the best practice description. About 15 years ago, the EPA looked at waste transfer station siting and identified, actually, I think in 2 areas that they studied intensely, that there was this concern that these waste transfer stations seemed to be turning up in low-income areas, and that there was some issues with the democratic location of these. And so that's the kind of stuff that we were trying to ferret out there.
Mm-hmm. Great. And can GIS help us with LCA assessment of water use?
You know, as I commented earlier, we don't often consider the spatial nature of our environmental impacts. And I would say in terms of impact on locally on water and land, it's actually pretty important. When we put things into the atmospheres, we can expect they spread out fairly easy, but they definitely don't in most other cases. So there probably is a need to consider the concentration of things. You know, there's a big difference if you put a kilogram of toxin in the ocean than if you put it in a small pond in terms of its impact. And I don't know that that is necessarily characterized in the traditional approaches with LCA. So I would hope that we could perhaps try to bring GIS into play in terms of understanding that better.
Okay. And are there GIS-based MCDA applications for sustainability analysis?
It's a fairly limited field, and I haven't extensively spent a lot of time with that myself, although I've worked with sustainability analysis independently of this. Lisa Lauren had actually directed me to work by Chris Mutel over in Europe on this area as one of the probably few people that are looking at sustainability analysis and life cycle assessment using GIS methodology.
Mm-hmm. And I have a question of how should an organization get started with GIS and MCDA for decision making?
I guess it probably depends on whether the organization is looking at making a specific decision discreetly or trying to build the capability. In terms of the latter, I mean, there's there are a lot of experts in the different fields. The problem is bringing them together, and I think actually the opportunity here is for better collaboration. A lot of specialization in GIS, lacking the subject matter expertise, perhaps in the particular topic of the decision, but as well in terms of decision-making, science, and operations research. So I would say that, again, if you're trying to build an organizational capability, is bringing those people together. If you're trying to make a discrete decision, then you can probably narrow your field and focus on trying to find the right method and perhaps the right people to help you do that.
Okay. Someone's wondering what on your title slide, what it is on the map that looks like it's on fire.
Oh, okay. Let me go there. There we go. Well, I have to admit, of course, I just went through my library of maps and I picked this out because I thought it looked pretty cool. But it is it is relevant to this. Actually, this is a transportation network for a region in eastern Pennsylvania, and I was providing some support to Rotary International. They were this is represented 5 counties where one of their districts is, and they were looking at where to site several new clubs. Their hypothesis was that transportation or travel distance was one of the factors potential members have in terms of deciding to become a Rotarian. And so I basically took the existing club locations and mapped out the travel times from every place in this area. And from that, the very bright areas are places where the travel times is distant. So you might think that in the darker blue areas, this might be a place where Rotary might want to put their next clubs. That was one of the outcomes from the work. But the second outcome was, and this is why I say this process doesn't give you the answer, it gives you information. The information was, it's pretty close to every club. So the hypothesis that travel time was an important consideration was really brought into question, and this probably points to the fact there's other more important factors they ought to be considering.
Mm-hmm. John, one person says, great presentation, and someone else says, are you available to support people trying to do GIS-based MCDA?
That's my thing right now. I worked in industry for a long time, and now I'm working for myself, and I am consulting in this area, yes.
Wonderful. Well, all your contact information was up on our website as well and on your last slide. So we have one more question, which says, how do you see the role of GIS-based MCDA evolving in the future?
Wow. It's a little hard to predict because it really is going to be driven by a lot of disruptive change, some of which we can guess at right now. So all the things you hear about the impact of big data is very relevant here. The ability to be able to gather it, process it, and crunch it is really key to this. Some of the things that are I would say, eminently involved in its future, though, is the fact that as opposed to this being something that we consider doing by going off and working at it manually for 3 months to get an answer, more and more the expectation is that we create methods and tools where we can get real-time decision-making support. And so that the access to that data, the processing of it, and conversion of it into some useful form is happening very quickly. Another thing is the nature of the data itself is changing. I talked about social media. That has had a profound impact, and it really is important. You know, when you just have a little bit of it, it's kind of noise. But when you have a wealth of it, it actually is really, really significant, and it has profound commercial and other useful terms. I mentioned things like looking at disaster response, emergency response, epidemiology, being able to access stuff right away and spatially visualize where things are happening in the world is really important. Remote sensing, it's not just coming from images that you download from the USGS or the Census Bureau now. You're getting stuff that is coming in almost real time or nearly real time. And if not, you go get it yourself. Drones are really going to have a lot to do in terms of gathering this kind of information as needed for various sources. So again, a lot of exciting related technologies are going to come together here, and I'm just kind of excited to see what happens. It's a little bit of scary stuff and a little bit of exciting stuff, a little bit hard to predict.
Yes, this is true. And what you've just described is quite overwhelming if you really start drilling down into it. But very enlightening presentation. We appreciate everything you've shared with us, and this webinar will be posted on our website for others to access if anyone would like to share it. And John, I thank you so much for sharing with us today, and we look forward to hearing more from you in the future.
Thank you.
Thank you.